hard problems like all the time, right? That's just the nature of computing. You know, all the various problems that computers tackle, you know, a certain proportion of them will be hard. And as computers become more powerful, faster, every year, those problems that are at the borderline between what can be computed in practical terms, you know, in terms of cost and time needed, that boundary keeps receding, you know, year by year as computers become more powerful. So, you know, thinking about those issues is something that would be on your mind. So these sort of these kinds of answers to this question, you know, what do you do when you're confronted with a hard problem? That would be interesting to you, right? Well, here's some suggestions. One is, you know, go to the root of the problem. Try to figure out what's the source of the hardness. Now, in general, in theoretical terms, that's impossible. But you can get clues and hints, and you might by being smart, ingenious, creative, you might be able to convert your approach to solving the problem in such a way that it changes the problem from being a hard problem to a much easier problem. Well, I'm jumping ahead a bit, but if you and we'll do examples of it in the course. If you can convert a hard problem well, let's say an NP. You don't know what that means. Well, let's assume you don't know what that means yet. But if you take a hard problem and you convert it into a much more ingenious approach, you might convert it then into a polynomial, a P-type problem, which is much more quickly solved. So by converting your problem, right, you may convert it from a hard problem to an easy, well, relatively, right, easier problem. Just, well, for example, if you can find algorithms, what's an algorithm? Well, we'll be talking about that a lot as well. An algorithm is just a step-by-step procedure, right? Do this, then this, then this, then this, right? An algorithm, like a recipe, like for cooking. But an algorithm is a recipe for a computer, for software, for your instructions. Do this instruction, execute this instruction first, then this one, then this one, then this one. That list called an algorithm, and that list, that algorithm, is eventually solves your problem if you've programmed it correctly. Okay. Another possibility. What can you do when you're confronted with a hard problem? Is you compromise. You get a less accurate solution to your problem, but the lower accuracy might allow you to compute faster. Okay, so you're trading off time for quality of solution. Right? Third one might be you just ignore it. You just push ahead anyway because. By the way, this is the mathematical sign for because. It's upside down. Therefore, like the therefore sign in mathematics is like 3 dots, but with a single dot above. So it'd be like dot dot dot. That's the therefore sign, and the because sign is dot dot dot. Okay, so this third possibility is effectively you just ignore the problem. You just forge ahead. You just plow ahead anyway, hoping that for the various forms of a particular problem and some variations, if you like, of that problem may be indeed very hard. You know, just require huge amounts of time. But other variants of the same type of problem might be relatively easy. Right? So you can solve them in a reasonable amount of time and effort. So this third option is just ignore that it's hard. Just go ahead anyway, right? Hoping that your particular variation of the problem is not one of the hard types. Okay? And a fourth option is just take a radically different computing style, right? Instead of like deterministic computation, you take a kind of randomized computing style. That's a bit vague. I'm not quite sure what he means by this randomized. Does he mean, for example, the Monte Carlo? Monte Carlo, that's a city, a gambling city in France, I think, on the Mediterranean coast of France. Is it? I'm not sure. Is it an independent city? Anyway, it's famous for its casinos, gambling casinos. So the Monte Carlo method is, if I've interpreted Sipser, the author, correctly, as an example of randomized computation. So by changing radically your computing style, the very model of computing that you're using, you might be able to simplify a problem, convert it from being a hard problem to a relatively easier problem. Okay, so that's a fourth thing. And just change your computing style. For example, use randomized computation, something like that. Yeah? And the point of doing that is just speed things up. All right. Okay. Now a remark here, especially now with internet commerce. My Chinese wife uses the internet a lot for her shopping. In fact, I think she does more business on the internet than she does, in pure money terms, than she does going out onto the high street with a shopping bag. She just gets stuff delivered. Now, to do that, she has to use her credit card. And people are not going to send their credit card number over the internet unless it was put into secret code, right? Secret code. In other words, secret writing. So, in other words, there must be software algorithms that convert her credit card number into some secret form that's called encryption, made secret, if you like. Crypto, like secret, graphy, write. So secret writing. So cryptography is the art of of converting sensitive or valuable information into some form that other people can't read, and at the other end, the receiver then decrypts. That's the opposite. Takes the encrypted message and decrypts it. In other words, converts it back to the original information, right? Like the credit card number. Okay. So now, why am I talking about this? Well, cryptography is the very opposite of the general direction of complexity theory. Complexity theory is trying to find ways, if you think about it, it's pretty obvious, to simplify programming. Trying to find easier, quicker, more efficient solutions to problems that you program. You get the computer to solve. So you're trying to make things easier, right, rather than harder. Now, cryptography is the other way, right? You're reversing the process. You're trying to when you encrypt, when you convert sensitive information into a form that's very difficult to decrypt if you're a third party, some enemy, if you like, or some thief who wants to steal like my wife's credit card number. So cryptography then is the art of doing the reverse of making things easier. You're doing just the opposite. You want to make things harder. You want to encrypt in such a way that some potential thief would have a harder time to decrypt. Okay, so there are the theory of complexity theory has helped motivated designers of new encryption codes, secret codes, that are virtually impossible to decrypt. Now, if you're not given the what is it, the password or the key. So complexity theory has helped increase the efficiency of cryptography. Right, it's had quite an impact on cryptography, and that's really important because the internet now is a major source of wealth in countries. Right, there's such a high proportion of a country's commerce, trade, is done now on the internet because there's a hugely greater variety of things to choose from that you can see online with all these vivid images nowadays, vivid graphics, and you get a greater variety of choice on the internet and more competition, which drives prices down. So you get a better price, you get better quality, you get greater variety to choose from. So more and more people are turning towards the internet to do their shopping. And the enabler of that were these modern encryption codes, which were motivated by computer complexity theory. Right? So that's one of so encryption or cryptography is one of the success stories of computer complexity theory. Okay. All right. Now we're going to a whole new sort of topic. So that was sort of this session. The previous one was sort of a general lead-in, flying over, what I call flying over the icebergs, an overview. Right. You're seeing sort of what's out there. Now we get into the next two sessions and a little bit here at the end of this one. I will change tack totally. I'll take off my overview hat. Oh, by the way, you may ask, why am I wearing this cap? It seems a little odd, especially it's like at night time. Well, it's precisely for that reason. Up there is a rather bright light, and it needs to be bright so that you can see the board, right? But I learned to my cost earlier in earlier sessions, well, earlier courses, that it was hurting my eyes. So I now wear a cap to shield myself from the eye-damaging glare of the light in the ceiling up here. Okay, so I just wear this American. I think it's American. It's American style. It's probably made in China. Like, isn't everything? That looks like a Chinese